In ancient Greece, 3 daughters of Apollo were known as the younger muses of the lyre, Niti, Mese, and Ipati, or as we Americans might say, Neat, Mese, and Hypate. Their names referred to certain strings of the lyre. Mese was the name of the string in the very middle, with Hypate on the bottom producing the lowest tone, and Neat at the top producing the highest tone. In ancient Greek music, the Mese was also the middle note of the heptachord, made up of 2 overlapping tetrachords. A tetrachord is a group of 4 descending notes, and the point or tone where they overlap is called the synnophy. This common tone, the synnophy, is what allows 2 tetrachords, which should total 8, to join into a heptachord of only 7 notes. The word Mese itself means middle, closely related to the ancient Greek word mese, meaning waist, the middle of the torso. The Mese in ancient music was of equal importance with the keynote in modern music. This was written by Charles Burney, an organist and composer who wrote a general history of music in the late 1700s. Burney went on to say that Euclid calls Mese the sound by which all other sounds are regulated. To say that the Mese was central to music is both an understatement and a pun. But regarding music, the word Mese means something more precise than just middle. It describes the exact center within a musical interval. Mathematically, the Mese as note can also be described as a mean, as it's the average and exact center between 2 musical frequencies. To find the mean of 2 values that form a boundary like a musical interval, you add the values together and divide the sum by 2. The mean will lie exactly in the middle in the position of Mese. The most well-known Mese note is the perfect fifth, which occupies the position of Mese between any octave. It first appears in the harmonic series as the 3rd harmonic, and as you can see, 3 is the mean of the octaves surrounding it, 2 and 4. We can see the Mese as a mean exactly dividing every interval in 2 throughout the harmonic series. Here the octave of C is successively divided by the Mese, starting with G, the perfect fifth, and subdividing down from there. But let's take an even closer look at this process. To generate a chromatic scale in the harmonic series, we follow this blueprint. It shows that the first note after the tonic, the minor second, is calculated by multiplying any tonic frequency by harmonic 17, or the number 17. The next note, the major second, is calculated by multiplying the tonic frequency by harmonic 9, and so on. So if we generate a harmonic scale off the tonic of A at 440 Hz, we can see on the grid line at the left that the first 3 notes of the scale form first a boundary of harmonic 1 and harmonic 17, and then divide that boundary with the Mese of harmonic 9. But while the 9th harmonic is Mese between the 1st and 17th harmonics, there's also a Mese created in the frequency values as well. The first harmonic, as our tonic, is at 440 Hz, which is calculated as 1 for the first harmonic times 440. The minor second, the next note in the scale, is calculated as 17 for the 17th harmonic times 440. We then halve, or divide by 2, this number until it falls within the octave between 440 and 880. The frequency value of the minor second, then, is 467.5. The next note, the major second, is calculated as 9 for the ninth harmonic times 440. We then have that number to reduce it to our current octave, and that frequency value is 495. The result is that 467.5 is a mean or Mese between 440 and 495. If we add 440 to 495, we get 935, half of which is 467.5. So here we have both a Mese dividing the harmonic positions exactly in half, as well as a Mese dividing the note's tonal frequencies exactly in half. And this is largely how the harmonic series works. Every note generated into the series is generated as a mean. The Mese function of dividing a boundary in half is based on the power of 3, so the Mese and its power of 3 create a triality within any duality, simply by dividing it. And it's this regulatory function of the dividing Mese that offsets and balances the power of 2 and its doubling octaves within the harmonic series. I explain all of this more fully in my book, The Next Octave. But the Mese can also create a hidden fourth, a concept John Dee described as a quaternary within the ternary. Here we see that a triangle reproduces 3 more triangles within each of its 3 vertices, but the designation of the Mese of each line segment creates a 4th triangle in the middle based on the central dividing position of the Mese. Ultimately, though, the Mese is embodied in the number 9. In Rodin's Mobius circuit, only one number occupies the Mese position, the 9. The other 8 numbers become boundaries or extremes of a mirrored pair. The lower octave of 9, half of 9 or 4.5, is the Mese of every mirrored pair on the circuit. If we flatten the boundaries of each mirrored pair onto a line, we see that 4.5 is the Mese value between 1 and 8, 2 and 7, 3 and 6, and 4 and 5. If we go up into the next octave, doubling the boundaries of 3 and 6 to 6 and 12, the 9 itself becomes Mese. The true power of 9, as Marco Rodin describes as the primal point of unity, is because of its position as Mese of all single-digit numbers, but more specifically, because of its position as Mese of the octave of 3 and 6. It sits at both the apex and the center, and functions as both the muse and the regulator of music. I'm grateful for any feedback. Please leave your thoughts in the comments, and thank you for watching.